Hi, I'm Alistair, I'm a games designer, and this is a new electronic game I've made, which I've called Orbital. So this is based on an arcade game called Cyclone, a reaction-based skill game, but I've made some modifications to make it more suitable for use in an escape room rather than an arcade. So there's an LED dot that moves around in a circle, and players have to press this button when the LED lines up with a target point, which is this glowing dot. Now, if I'm too late or too early, you'll see that you get a visual feedback. Half of the ring will light up red to show where your timing was off. And also, the speed of rotation actually slows down with every incorrect guess, making it slightly easier for players who are finding it hard. Now, when you get it correct, the LED moves on to the next innermost ring. We get a new target point set, and also notice that the direction of rotation has changed. Now, if I can, that was a bit too early. That was also too early. There we go. And if I am able to solve all three rings correctly, what happens is a relay is activated, which releases a maglock and opens a panel on the plinth underneath from which players can access their prize. You get a short animation sequence, and then the puzzle automatically resets and the lock relocks again. Now, there's loads of ways to customize this. You can change the shape of the orbits. These don't have to be rings, they could be horizontal strips with the LED bouncing back and forth. Or you could place individual LEDs in an arbitrary path. You can change the speed of movement of the LED, the number of targets. You can make a sound effect play as an audio cue every time the LED passed over the target. And because these are programmable RGB strips, you can change the colour palette to make the dot represent a comet orbiting a planet, or a particle orbiting around an atom, or anything you want. And in the rest of this video, I'm going to explain how you can make this yourself. So this is just 5mm plywood board, which I sprayed with this textured spray paint to give it a stone effect, and the same with the plinth behind. Now, originally this panel was actually mounted on top of the plinth, but I've removed it just to make it easier to show you the components on the reverse. And this is what is powering the puzzle. So the LEDs themselves, I'm using 3 LED rings of different numbers of LEDs in each, and these are using WS2812B programmable LEDs. I've used them lots of times. You could use a different LED controller, but the reason I like these ones is that they operate at 5 volts. They're very easy to control from a single pin of an Arduino, and they're cheap and very easy to buy. And the way I've got them wired up is that I've got a single pin of the Arduino wired into the data in of the outermost ring, and then I've got the data out from that ring going to the data in of the next, and the data out from the middle ring going into the data in of the innermost ring. So these are all wired in series, which means as far as the Arduino is concerned, this is effectively one single continuous straight line of LEDs. The logic that separates them into these 3 different rings is actually all handled in the code, which I will show you in a moment. And so I cut grooves into the plywood to insert the rings, and then on the front side of the board I've 3D printed these plastic diffusers and inserted them just to give the light a little bit of a softer glow. Now here's the arcade button, which we're using for the input. That's wired to another one of the GPIO pins on the Arduino, and I've also got an LED in there which lights up just to give you a little bit of feedback on the button itself as well as on the rings when the player makes an input. And then I've got a 5-volt relay module as well. This is being triggered by another GPIO pin on the Arduino, and that is controlling power to the maglock, which is located in the plinth. So if I now just solve the puzzle, if I can actually get it correct, there we go. That triggers the relay, which releases power to this maglock here, and that is what is securing the plinth door. And then when the puzzle resets, this gets re-energized again, so you can simply reset the puzzle by closing the door again, and that is reset, ready for the next playthrough. And here's an illustration of how those components are wired together using a fritzing diagram. So it's pretty straightforward. I've got my Arduino Nano here. We've got the button wired to pin 3 and ground. I've got the relay module wired to GPIO pin 5, ground and 5 volts. And then here we've got our Neopixel or WS2812B LED rings. So the outermost ring, as I described, is going to pin 2. I've got a 330 ohm resistor in series on that line. That's always best practice whenever you're sending a signal from a microcontroller to one of these rings. Put a series resistor somewhere between 300 and 500 ohms in series before the first LED. And I've also got a capacitor across the 5 volt and ground lines just before the LEDs as well. These LEDs can draw a surprising amount of power. Each one of these LEDs has both a red, a green and a blue component to them. So if you light all 3 RGB values up to full intensity, they draw about 20 milliamps each, so that's 60 milliamps for just one LED. Now, depending on the sort of light pattern you're trying to display, that obviously means that your total power requirements are going to be slightly different. But in this case, I've got a 5 volt DC input here, and this is what is supplying power to the relay module, to the Arduino, and to all the rings as well. I'm actually using a 10 amp 5 volt DC supply, which is probably a little bit overkill, to be honest. There's no way you need to use that much current. But if you're noticing that your LEDs are dimming a bit, what tends to happen is you get kind of a pinkish or a yellowish effect, or the colors are displaying incorrectly. That can be a sign that you are not supplying enough current all the way through the LED rings, and that you might need to use a better external power supply. As I said, they're all connected in series, so the data line that's coming from the Arduino goes all the way around the first ring and then out through the data out to the data in of the middle ring, all the way around and then to the middle ring. And I've got the 5 volt and the ground lines shared between them. And then on this side, I've got my maglock, which is wired to a separate 12 volt DC power supply here. And that is wired through the common and normally closed terminals of the relay module, so that the Arduino is able to energize or release the maglock when the puzzle is solved. And this is the code that is running on the Arduino. Now, this is a relatively long code listing. Now, a lot of it is fairly standard stuff, which if you've been following this channel for a while, you have seen me use these kind of coding patterns before. So I don't want to spend too long looking at those. Also, some other parts of it are relatively specific effects which I've implemented, just like the explosion or the lighting up, and you might want to change those for other effects instead. So I'm going to sort of skip over some of the less interesting or the very more specific bits and just describe the more important mechanisms in a bit more detail. So we'll start at the top anyway. I'm using the fast LED library, as is very common whenever I want to control programmable LED strips. You can download it from there. And then we define some constants. So these are the GPIO pins, which I just described in the wiring diagram, are connected to the different components. And we have a little bit of configuration of how we've got those LEDs set up. So I'm using 3 rings. So I say I've got an array with 3 elements, and these are the number of LEDs in each ring. So I've got my outermost ring has got 60 elements. I've got 40, 24. There's no reason for them to decrease in size. Well, I mean, there is if you want them to fit inside each other, as I have done. But you could have any number of rings or strips, and with any number of LEDs in each, you just need to change these values here. I'm also going to create a constant here that is simply the sum of all of these values here, because there will be some effects which I want to apply to all the LEDs in total rather than to the ones in a particular ring. I've hard-coded the target values to be the midpoint of each ring. So in the 60 ring, the target will always be at position 30, and likewise with the 40 and the 24 LED ring. If you wanted to, you could calculate an arbitrary target each time the game was played. In my case, because I've actually rotated the rings slightly when I inserted them into the panel, the targets don't exactly line up anyway, but I wanted them to be approximately in the middle. So that's why I've chosen these values. You can set anything you want. And then this is, as I mentioned, I hope this came out in the video, that every time I made a mistake, the LED actually slowed down a little bit. And specifically, it stayed for 5 milliseconds longer, so 5,000ths of a second on each LED before progressing to the next. So if you increase this value, it will actually make the game slow down at a faster rate with each incorrect entry that players make. And if you don't want it to slow down at all, obviously you can set that to 0 or comment out the code later on. Then we have some global values. So I've got my array of RGB LED values. Obviously that has one element for every LED, so that is equal to the total LEDs I've got. These are some game values. So current ring is a little bit like the level of the game we're up to at the moment. It starts at 0, which means the outermost ring, and it's going to increase with each correct entry that the player makes. The current LED that is being lit up in that ring, well, that also starts at 0. And direction, I'm going to keep as either 1 or -1 to indicate whether the LED is moving clockwise or counterclockwise. In the version of the game which I displayed in the video here, I simply made it continue in a given direction for each ring, and then it reverses direction with the next ring inwards. In a previous version of the game, I actually had it so that the LED bounces backwards and forwards within each ring as well, which you could also do if you want. So to do that, you simply set direction to 1 or -1 every time it reaches the first LED or the last LED in each ring. I'm also going to keep track of a boolean called button pressed. Now, the way that I'm handling the button input, in a simple Arduino sketch, you might use polling to detect when an input has been made. So that means in each iteration of the loop function, you use a digital read and you compare whether the value read on the GPIO pin that the button is connected to is high or low. And that's fine, and that works for a large number of projects. In this project, I'm actually doing something a little bit simple because we're doing all these animated effects and we're updating LEDs and we're making them fade out and things like that. These all take time for the processor to do, which means that the loop function has sort of gets delayed. It's got other work to do to keep the game running. And there's a risk that if you only checked for the input once each time at the beginning of loop using a simple digital read, you might not catch the button input. Now for this game, or for any other game that's kind of reactions based, that you want to make sure that definitely you catch any inputs the moment they happen, it's a better idea to use what's called an interrupt. An interrupt does exactly what it sounds like it does. It interrupts the process from doing whatever it's doing and kind of injects a new bit of program to run at that point before it then carries on with what it's doing. And we are going to use an interrupt to read the button input. So I've got some button variables here. You'll also notice I've got a volatile variable here. That's because it's a value that's going to be used within an interrupt service routine. I'll explain a bit more exactly how that works in a minute, but that's what these two global variables here are doing. And we'll also we'll keep track of the last time the LEDs were refreshed, the last time the button was pressed, and also how frequently, a little bit like the frame rate of the game, I guess you want to think of this as. Again, these are all measured in milliseconds. So if you want things to happen faster or slower, you can adjust these as you want. I'm going to define a palette, an RGB palette. This is a type of structure that is defined within the Fast LED class. Fast LED is a brilliant library. It's got loads of examples that give you examples how to create rainbow effects and fire particle effects and lots of other things as well. But I'm using a relatively simple function, which is simply a gradient palette that fades between a start and an end color. And that's how I'm going to create that kind of greeny blue effect at the start and the end sequence. I mentioned that one of the ways you could theme this game was to have a comet orbiting around a planet or something like that. So let's say you wanted to have a heat map gradient that went from like a intense white through yellow and then orange and red before fading out, you could also define that using a palette like this as well. So I've got a gradient palette there as well. Okay, then we go on to the setup function. So this runs once when the code first starts. I initialize the serial connection just for debugging purposes. I initialize the LEDs. So this is the type of LED I'm using. They're connected to LED pin, which was pin 2 as defined at the top of the code. And this is the color byte ordering for a WS2812B strip. You might be used to RGB, but actually the strips I'm using are GRB value instead. Again, if you tell the strip to light up red and it actually comes out blue or something similar to that, you might need to tweak those values there to get it to come out correctly. I'm going to set an overall brightness of the LED strip to moderately bright, but not excessively so. I find that personally I couldn't tell much of the difference between that value all the way up to 255, and it will draw a little bit less current if I reduce it slightly. And then I'm going to define my palette. So I've actually got 4 different values in my fading array, as you can see here, and I've defined them using a hue, a saturation, and an intensity value as well. So these are not RGB values here, so this doesn't mean green and blue. Rather, these are different shades within the bluey green range of the color spectrum, because I'm using values between 100 and 140, all with full saturation and then reducing intensity. So this is going to kind of give me I kind of wanted an aqua-ish effect, which I thought was going to work well with the grey stone texture which I'd applied to the wood. We initialize the button input, and this line here is pretty standard. I hope you're used to this. We're connecting a button through to ground from the GPIO pin, so we activate the pull-up. This is the bit that I can't remember if I've used this in a previous project or not, but certainly you might be less used to seeing this method here. So we're going to attach an interrupt, as I mentioned, to listen on the button pin. And I should mention that you can only attach external interrupt functions to certain pins. I think it's pins 2 and 3 on an Arduino Nano. I'm using pin 3, which I know is fine. I don't think there's any others. Different microcontrollers have interrupt capabilities attached to different pins, so you need to make sure you're using a pin which is capable of handling an interrupt. What are we going to listen to? We're going to listen to a falling edge on that pin, and that means that the state of the pin was high, and at the point it falls to a low value, which is going to happen when the button is pressed, because remember it's an input pull-up, so by default it's high because there's a pull-up resistor that's pulling up to 5. When we press it, it falls down to ground, which is what the other side of the connector to the button is. So when it falls, we're going to call this interrupt service routine button ISR. Now, that is at the bottom of the code. That's here. So what does button ISR do? Well, it reads the current timestamp, the current millis, and it compares that to the last millis, so the last time the button was pressed, and if more than 200 milliseconds has elapsed, it's going to set the button pressed variable to true. So this is a simple debouncing method. This simply makes sure that we don't count 2 button presses in very short succession. As the mechanical switch engages, it sometimes clicks on and off a few times. But we want to make sure that we don't catch more than 2 falling edges in a 1/5 of a second period. We update the value of the last time that we did record a button input, and all we do is we set this button pressed variable to true. We don't actually perform any other logic. We don't check what position the LED was on. We don't light the LEDs or activate the relay or something like that. All we do is set a value to be equal to true. And this is something really important if you're not familiar with interrupt routines. These little kind of snippets of code that can be injected at arbitrary points in the program execution whenever this event is captured. So when the button pin falls, we're basically telling the code to ignore what you were doing before, or not ignore it, but put it on hold, basically. This code execution could be anywhere in the middle of this loop function here. It's just about to do this thing here. But, hang on a minute, the button pin has just fell. What we're going to do is we're going to run this button ISR code before coming back and carrying on where we're up to in the loop function. And because the way it the way that the processor handles this, it's really important that whatever you do in an ISR function is very short and quick and doesn't, it's literally like an interrupt. Imagine it like an interjection. You're just shouting, well, stop, do this quickly, then carry on, okay? So all we do is set a Boolean variable. We'll actually apply the logic of what happens when that Boolean variable has been set in a moment. Okay, so back to setup. So we've attached that ISR, and once we've done that, we basically don't have to think anymore about handling the input at all, because it's going to be done sort of automatically for us whenever that pin falls. We activate the relay pin that's going to energize the relay and release the maglock as normal, and then we do a little a light show, as I've called it here. So and these are the kind of the effects that you can really play around with and theme however you want to make this an interesting visual aesthetic for whatever game you want to use this in. What I'm going to do is I'm going to loop over this function 300 times. I'm going to fade to black by. This is a function that's defined by the fast LED library again, and it causes a really nice smooth fade out of all the LEDs in the strip. So it's nearly like a blur effect kind of thing. A lot of the time LEDs can look quite harsh because if they just flash on or off, they're kind of a very harsh digital output, whereas we want them to be like smooth and glowing. So we're going to fade them out first of all, and this will fade everything that was lit by a fraction. So you can increase this fraction to make them fade more or less. Then we're going to choose a random LED that is somewhere on the strip. So we choose a random number between 0 and the total number of LEDs, and we're going to light that LED up. Again, a random color that is somewhere around the hue of 100 up to 148, but somewhere lying in that range with a pretty good saturation, high intensity. Then we're going to update the strip, delay by 10/1000th of a second, and then we're going to do that again. So we're basically going to light up 300 randomly chosen LEDs, a hue somewhere in the greeny blue spectrum, but every time we light one up, what we're also going to do is we're going to fade all the others out, and this will create like a really nice kind of twinkly effect. But like I say, you can fiddle around with this however you want just to create something. This just runs once when the code first turns on, so it's basically like a startup sequence if you want. And then once we've finished doing our pretty display, we'll fade all the LEDs out, so we're ready to start the game. The fade out function itself is defined, that's defined a bit later on as well. So this simply fades out all the LEDs gradually until they are sort of reset. So it's like a reset function basically. Okay. Where were we? We were back at the top. Okay, so now we're on to the loop function. Here we go. So this is the main program loop that just runs over and over for as long as power is being supplied. So we'll grab what the current time is, and as mentioned, that's going to get used in the interrupt service routine function to debounce and make sure we don't record two inputs in the same space of time. But it's also going to be used in this function to update the LEDs. So the frame rate at which the LEDs are updated depends on comparing the current millis time to the last time they were updated and checking that that update interval or greater than that update interval has elapsed since the last time. If so, what we need to do is we need to, based on the current ring, so the current level of the game we're up to, we need to kind of count how many LEDs along the strip we are. Remember I said that the Arduino is treating this as one continuous line of LEDs in a row, and we need to work out whether the first LED in the current strip is. So I've defined a helper function here called calculate ring offset, and what that does quite simply is to, if I can find it, here we go, it counts through all of the rings that have been defined and it increases a total here, total value that starts at 0, will increase that total by the number of LEDs in the ring until we get to the ring that we're currently on. So if on the first ring, offset's going to be 0. If we are on the second ring, based on the number of rings I've defined here, we'll be at LED 60. If we're in the next ring in, we will be at LED 100, because we'll simply count this offset based on how many LEDs we've already covered in the ring. So that gives us a ring offset. What we're then going to do is we're going to move the comet, as I've called it here, within the current ring. So we call the move comet function, and this is the starting LED of the ring we're in. We will advance it in the direction it's currently moving. So remember, direction is either +1 if we're going clockwise, or -1 if we're going anti-clockwise. If we get to the last LED in the ring that we're in at the moment, we reset the current LED to 0. Or if we were going backwards and we've gone less than the first LED in this strip, we'll reset back again at the end. So this is a wrapping function that just ensures that we stay within the ring that we're in at the moment. Then, having done that, we need to update the colors in the ring. So we'll call the update LED colors function, and that is here. Once again, we fade to black by. I don't simply set all of the LEDs to black, because if I did that, I would have no trail behind the comet at all. It would be a single dot moving around the ring. And perhaps that's the effect you want to have. In a sense, it makes it more precise, but I think it makes it a little bit too basic. I much prefer to have this gradual fading trail. So again, I call fade to black by to get this lovely smooth fade out and glow. And then what we do is we light up the LED that is the current position of the comet. So that is the ring offset, that's the number of total rings we've already completed, plus the index of the LED within the ring we're in at the moment. And we want to light that up white, but again, if you wanted to put a different color for the dot that is moving around, you can just change that to any value you want. You can either call a HTML color code value like white or red or green or light blue or Alice blue or whatever, or you can use an RGB value or an HSV value here as well. And we also need to draw the target that we're aiming for the player to stop this LED on. So here I'm using another built-in function of the fast LED library. This generates a sine wave at a given rhythm, at a given tempo essentially. So this is at 30 beats per minute. It will generate a sine wave between the values of 64 and 255. And I'm going to call that my beat. So my LED is going to glow 30 times a second on and off basically. And then I'm going to use a hue, which I've set to a slightly different BPM. It's slightly slower, so that essentially my color changing hue and my pulsing intensity are slightly out of time with each other. So it's not always that the green is the bright one and the blue is the dim one. They're going to be out of time, so you'll get a nice effect there. And then what I'm going to do is, just as we lit up the current LED white here, what we're going to do is we're going to light up the target LED in the current ring based on the hue and the beat, which are chosen by these sine waves here. And this is how you get another nice little glowing effect. The only exception to this, however, is if the comet is right over the target at the moment, we're actually going to override the value that was going to be set here, and we'll make it full brightness instead. So instead of having this pulsing in gradually, we'll actually just illuminate it bright. Again, at one point I actually had this hard-coded to be red, so that when the comet passed over the target it lit up red. But I actually found that a little bit confusing, because I'm also using red as an indicator for when the input was incorrect, and I didn't really like it to have two different meanings. Maybe I could have lit it up blue or orange or something instead, but what I've done instead is I've kept the colour it was already on based on the glowing rhythm here, but I've just made it full intensity instead. Okay, so we update the colours in the LED. We've moved the comet around, we've updated the colours. We actually send the updated values of the LED array to the strip. That's what show does. All of these functions we've been looking at here so far have been setting values in the LED's array, which we defined at the top, but you always need to actually remember to push that array out to the strip, and that's what the fast LED.show function was. And finally, we actually need to call the input. And so if button pressed, now remember button pressed was this Boolean value that was being set in the interrupt service routine. This is pretty much the only thing the interrupt service routine actually did, was set the value of this button pressed variable. And now we need to actually apply the logic that acts upon that variable. So within the loop function, here we go. If the button is pressed, we call handle button press. All right, so let's see what handle button press does. Here we go. So we're going to clear the flag. This is the flag that was set by the interrupt service routine so that we only act upon it once. Next time the button is pressed, we need to have reset that flag again. We will once again calculate the offset of the ring we're in, and now we need to work out if this button press was on time or not. Now, it took me a little bit of time, I have to admit, to actually come up with the correct logic for this. I don't know why I found this so hard. If we are in a ring that is rotating clockwise and the current LED is less than the index of the target LED, that means we're too early because we haven't got there yet. But you're also too early if you're rotating counterclockwise and the current LED is greater than the target LED, because in that case you started off at a higher value and it hasn't yet dropped low enough. So those two are the two cases for when you press it too early. When you press it too late, well, that's when it's going clockwise and you've already shot past the target LED, or you're rotating anti-clockwise and you have already gone under it. In both of those cases, you're too late. And then which section of the LED ring you light up then depends on whether you were going clockwise or anti-clockwise as well. So if you're going, if you're going clockwise and it's too late, you want to light up the second half of the ring. If you're going anti-clockwise and it's too late, you light up the first half, and then the opposite for is early and the other way around. So this took me a surprisingly long. There probably is a more elegant way of writing this, to be honest, but this is correct, and I found the way that the logic was written here was the easiest way to follow this. But if you have a more efficient or elegant way of writing that, do please let me know. It feels like it shouldn't have been that hard. But all this does, like I say, this lets the code calculate whether the input was correct or not, and also does the visual output of failure by calling this indicate failure function here. So we'll pass a message, which we'll just put for debugging purposes. We'll pass the ring offset again, so just this counter of how far we are through the game, and which LEDs we want to light up based on the input. So that gets passed to the indicate failure function here. So we'll serial print the message, light up the LEDs, call the fast LED show function, and we'll just do that for 1/10 of a second, just as a brief flash. And this is the line of code here where we modify the rate of update of the game to make it easier if players get the answer incorrect several times in a row. Otherwise, if we were neither too early nor too late, well, that means that we must have been bang on target, and in that case we call indicate success instead. So this is what happens when the game is successfully completed. We'll put on target. We'll call this complete ring function. Again, this is just a visual effect. You can play around with this and do whatever you want to instead. But what I did was I created kind of an explosion effect that emits outwards starting from the target point and kind of goes to complete both sides of the ring starting from that. So to do that, we calculate a radius that starts at the current LED and proceeds both anti-clockwise and clockwise from it. We make sure we don't exceed the total number of LEDs in the ring and go on to the next one. So that's why I'm using the modulo function here, just to make sure we don't bleed onto either of the previous rings. And then what we do is we map that color palette, that nice color palette we assigned at the top of the code, and we will blend going outwards from the starting LED all the way to the final point of the palette using a linear blend. So this is, again, these are all just functions which you can look up more of in Fast LED. I don't want to go into a lot of detail of them here because they're quite specific, but you could just light them up a block color if you wanted to, or you could do some sort of pretty chase pattern, whatever you wanted. This is just for player feedback when they complete one of the rings. If the ring they completed if there are more rings still to complete, what we do is we go on to the next ring. So we advance the index that says the current ring number we're on. We reset back to the first LED within that ring. We modify the direction if you would like to do so. So this thing about swapping clockwise and counterclockwise with each level, this is the line of code that does that. We'll reset the update interval. So if the player had made several incorrect attempts on this ring, this update interval would have been increased a few times already by this line of code here. So if we want to reset that back to the initial speed for the next level, we do so here. And we also just cancel the flag for the button pressed. Otherwise, if they've just completed the final ring and that there are no more rings left to complete, well, that's the end of the game. So we call celebrate win, mainly a visual effect that just lights up pretty lights, but importantly, it also writes a low value to the relay. That's what's going to energize the maglock, and that will stay low for the duration of this little celebratory effect. When that is finished, however, we then call reset game, and reset game, unsurprisingly, resets the maglock, so re-energizes the relay, which secures the 12-volt power supply to the maglock again, goes back to the first ring, the current LED, and also the initial direction. So we're back to all of the default values we had at the start of the game, and it is ready to play all over again. And that's it. So that just about brings me to the end of this video. Thank you very much if you've made it this far. This is not a typical escape room puzzle. It requires dexterity and reaction speed, whereas you might normally associate escape rooms with more logic and deduction. But escape rooms are team activities, and different sorts of puzzle types appeal to different sorts of players. So I think it's really important to have a variety of puzzle interactions in there so that every player can feel they're bringing something to the team. Now, as always, I will put the code download and the wiring diagram for this project in my Patreon account, and I'll put a link to that in the description below. So if you'd like to head over there and download the resources to build this project yourself, or any of the other projects which I've featured on this channel, do please head over there and check it out. Other than that, if you've got any questions or comments or suggestions or ideas about how you could theme this kind of puzzle to fit in with different sorts of escape room scenarios, I'd love to hear them. So do please write them in the comments below as well. And other than that, I just want to say thank you all very much for watching, and I look forward to seeing you next time. Okay, cheers, bye.